Hello students, today I am going to explain a very important theorem known as Rolle's theorem. The statement is, if a function f from closed interval a comma b to r such that the function f is continuous in the closed interval a comma b, the function f is differentiable in the open interval a comma b, the function f of a equal to f of b, then there exists at least one value of x, say small x, that is x equal to c belongs to the open interval a comma b, such that f dash of c equal to 0. The proof is very simple. Already they have given in the statement that given the function f from closed interval a comma b to r is continuous in the closed interval a comma b. If a function continuous in the closed interval a comma b means the function must be bounded. The function f must be bounded in the closed interval a comma b. The function f must attain its bounds in the closed interval a comma b. There exist infimum and supremum, say small m and capital M, such that small m less than or equal to f of x less than or equal to capital M for all x belongs to the closed interval a comma b. Since the function f attains small m as well as capital M, let small m is attained by the function at x equals to c belongs to the open interval a comma b, and let capital M is attained by the function at f equals at f, that is x equals to d belongs to the open interval a comma b. Means if a function is continuous in the closed interval a comma b means the function must be bounded. If it is bounded means if already it attains the bounds, that is small m and capital M I had taken, that is infimum and supremum, that is small m equals to f of c and capital M equals to f of d, because they have clearly mentioned in the statement that the function f is continuous in the closed interval a comma b. Any function which is continuous in the closed interval a comma b means it must attain its bounds, that is infimum and supremum, that is I have mentioned clearly here. Now case 1, if small m is equals to capital M, that is infimum is equal to supremum, and f of a equal to f of b, then f of c equals to f of t, that is here small m equals to capital M and f of a equal to f of b. If the value if this condition holds good, then the function f must be constant function, that is f dash of x equals to 0 for all x belongs to the open interval a comma b. You can see the graph I have mentioned clearly. Hence the theorem is proved in case 1. In case 2, now consider case 2. Let capital M is different from both f of a and f of b, and f of a equal to f of b. In this case, f of a and f of b is here. Capital M is different from f of a and f of b. Here f of a value come and here only f of b value come, that is f of a equal to f of b. So capital M is not equal to f of a and capital M is not equal to f of b, that is capital M earlier I mentioned clearly, that is f of d is not equal to f of a, and f of d is not equal to f of b, that is d is not equal to a and d is not equal to b, then a is less than d less than b. Since the function f is differentiable in the open interval a comma b, that is clearly mentioned in the second condition, the function f is differentiable in the open interval a comma b, then it must be differentiable at d, because d is lies in between a and b, therefore it must differentiable at d, that is the f dash of d exists. Now I will consider three cases. First case is you can see the graph here, f dash of d greater than 0, that is the function f is increasing function, at D there exists delta greater than 0 such that f of x greater than f of d for all x belongs to d comma d plus delta. F of x greater than capital M, I have substituted f of d value for all x belongs to d comma d plus delta, which is a contradiction because capital M is the supremum but the function value is greater than capital M. It is not possible, therefore which is a contradiction. Now I will consider the case f dash of d less than 0. That is, you know that f dash, any function that is derivative less than 0 means that is a decreasing function. You can see the graph here. There exists delta greater than 0 such that f of x greater than f of d for all x belongs to d minus delta comma d. F of x greater than capital M for all x belongs to d minus delta comma t. Again we got the contradiction result because supremum is the upper bound but the function is greater than upper bound, which is a contradiction. It is not possible. The third case I will consider f of d equals to 0. The third I had considered already f dash of d is increasing, f dash of d decreasing. In both cases I got a contradiction result. Therefore the C, that is third one is, that is you can see this graph at the point D derivative is 0, hence the theorem is proved in the case 2 because in this case all the three conditions satisfied, that is 1, 2 and 3. Both three conditions are satisfied. Now consider another case, that is let small m is different from both f of a and f of b and f of a equals to f of b. That is small m equal to f of c and f of a equal to f of b. The value will come here. That is small m is not equal to f of a and small m is not equal to f of b. F of c is not equal to f of a and f of c is not equal to f of b. I have substituted small m value, that is f of c. C is not equal to a and c is not equal to b. A less than c less than b. Since the function f is differentiable in the open interval a comma b, then the function f must be differentiable at c. That is f dash of c exists because second condition they have clearly mentioned that the function f is differentiable in the open interval a comma b. Therefore c is lies between a and b, that is f dash of c exists. Now I will consider three cases. First case, second case, third case. If f dash of c is increasing function at c, there exists delta greater than 0 such that f of x less than f of c for all x belongs to c minus delta comma c. F of x less than small m for all x belongs to c minus delta comma c, which is a contradiction because you can observe the graph. Small m is nothing but infimum. The function value less than infimum, which is not possible. Again contradiction result. If I consider if f dash of c less than 0, that is the function f is decreasing function. At c there exists delta greater than 0 such that f of x less than f of c for all x belongs to c comma c plus delta. F of x less than small m for all x belongs to c comma c plus delta. Again which I got a contradiction result because small m is nothing but infimum. The function value will not be less than infimum because infimum is the lower bound. After that I will consider third case, that is if f dash of c equal to 0 at the point c the derivative is 0, hence the theorem is proved in this case because in this three condition is satisfied. First condition, second condition, third condition, at least one point we will get at that f dash of c equal to 0. More than one derivative we can get that at that derivative the function is 0, but at least one we will get it. Again I will tell you once again, explain you once again. So Rolle's theorem is they have given three condition, that is the function f is continuous in the closed interval a comma b, the function f is differentiable in the open interval a comma b, then the function f of a equal to f of b. So first clearly observe the statement. They have given three condition and they have they are telling that at least one point we will get, at that point the derivative is 0. You know that if a function is continuous in the closed interval a comma b, it means it is bounded function. If it is bounded means infimum supremum must exist. So I had taken small m equal to f of c and capital M equal to f of d, and small m is less than or equal to f of x and less than or equal to capital M. This is the relation for all x belongs to the closed interval a comma b. In the first case I have considered if small m equals to capital M, I got this result, that is I got the constant function, that is hence the theorem is proved in this case, because if you observe all three conditions is satisfied. Again I have considered let capital M is different from both f of a and f of b. Again three cases I had considered. After that I had considered small m is different from f of a and f of b. Again I had considered three cases. I hope you understood. If you have any doubt, please comment. Thank you so much for your valuable time. Thank you, students.